Hello my dear students, I warmly welcome you to CR Digital Classes. So now in this lecture, we are going to discussing about the continuation topic, second subtopic in unit 4. Okay. In the previous lecture, we discussed that method of variation of parameters, that is the first subtopic in this unit 4. So now we are going to discussing that second topic. Name of that topic is linear differential equations with non-constant coefficients. Okay. So the problem which we are going to solve based on this method, that method is called the reduction of order method. By using this reduction of order method, we can solve the problems based on the linear differential equation with non-constant coefficients. Okay. So first of all, what is that linear differential equation with non-constant coefficients, and what is the procedure, and what is the general solution? So everything detailing we are going to discussing in this lecture, and whatever the question we are going to discussing now, that question repeated so many times in the examination recently in 2023 June July question paper also this question asked, no? Very important question. Okay, so observe carefully. Question: given that small y is equal to small x is a solution of the given linear differential equation. Okay, why? Because here it is a order of the differential equation is 2, highest derivative occurring on this equation is 2. Okay, so highest derivative occurring on this equation is 2, but the degree of that equation is 1. Okay, so that's why we are calling it as a linear differential equation with non-constant coefficients. Here d square y by dx square coefficient is x, dy by dx coefficient is small x. Okay, and here you have small y. The coefficients are non-constant values. Non-constant means in variable format, x square x. So that's why where x naught is equal to 0, then find the general solution of the given equation x square d square y by dx square plus x into dy by dx minus y is equal to small x. In this problem, you have two differential equations. The first equation is a homogeneous differential equation. Okay, this is called homogeneous linear differential equation. Homogeneous. Okay, for this homogeneous linear differential equation, what they are saying, y is equal to x is a solution. For that homogeneous linear differential equation, already y is equal to x is a solution. Now with the help of that solution, we have to find the solution for the non-homogeneous equation. For the second equation, we have to calculate that another solution. That another solution is called here general solution of the given differential equation. Okay, so therefore observe carefully. Given second order differential equation is x square into d square y by dx square plus x into dy by dx minus y is equal to small x. Okay, that second equation we are taking as equation number 1. Equation 1 is of the form second order differential equation with non-constant coefficients. Second order, clearly you can see a second order. Okay, highest derivative occurring in the given equation of 1 is second order. So therefore that is a second order differential equation with non-constant coefficients. You know very well here coefficients as variables, x square and x instead of the numbers. Now this equation number 1, you have to compare the general form of the linear differential equation with non-constant coefficient. That is mentioned in this box, that is given by equation number 2. Okay, so the general equation means you can take nth order, but in our problem we required only second order. So that's why we are taking the second order general equation of the linear differential equation, that is f suffix 2 of x into d square y by dx square plus f suffix 1 into x of dy by dx plus f suffix naught of x into y is equal to q of x, where the leading coefficient f suffix 2 of x is always not is equal to 0. What is that leading coefficient? The highest order derivative is there, na? That derivative coefficient is called a leading coefficient. That leading coefficient is always not is equal to 0, then only we can call it as a second order differential equation. Okay, so this above equation number 2 simplest form we can write in the operation format, f2 of x into y double dash. You know very well d square y by dx square value we can write simply y double dash. D square y by dx square we can write simply as y double dash. Okay, double derivative of the given function. Next to plus f1 of x into dy by dx value, we can write f dash plus f naught of x into y is equal to q of x. Equation number 2, you can write in the original form in this format or this format. Both equations give the same meaning. Okay, and from the given data we have homogeneous equation of equation number 1 is equation number 1 is not an homogeneous, it is a non-homogeneous. Why? Because you have that RHS value x algebraic function you have. Okay, for that non-homogeneous equation, homogeneous equation is given by x square y double dash plus x into y dash minus y is equal to 0. That is taking as equation number 3. Okay, so what is the reason to take that homogeneous equation? Why? Because in the problem, so where f2 of x, non-constant coefficients, first we are taking f2 of x is equal to small x square. Compare equation number 1 and equation number 2. Then you will get the value summa f1 of x is equal to small x and f naught of x is equal to minus 1. Okay, suppose that given y is equal to small x is a non-trivial solution of equation number 3. For any homogeneous differential equation, whenever they mention particularly y is equal to x is a solution, that is a non-trivial solution. Non-trivial solution means not is equal to 0. Trivial solution is nothing but you can take sometimes y is equal to 0. Non-trivial means it always not is equal to 0. Solution of equation number 3. That is, so in this method in the method of order of reduction method, so the given solution, whatever they mention in the problem, you have to take that solution as y suffix 1. Okay, y suffix 1 of x is equal to small x. So therefore, that implies if y suffix 1 of x is a solution of equation number 3, then definitely it has to satisfy the equation number 3. That is only in a condition. So from the given problem, we have y is equal to x is a solution of equation number 3. So according to our procedure, we are taking that y value y1 of x. y1 of x is equal to small x. If it is a solution, definitely it has to satisfy the equation number 3. So substitute wherever you have y in equation number 3, y suffix 1. Okay, so therefore in equation number 3 here we have y suffix 1. So wherever you have y suffix 1, just to substitute y suffix 1 So therefore after substituting y suffix 1, you will get in this format x square y suffix 1 double dash plus x into y suffix 1 y dash minus y suffix 1 is equal to 0. Just in place of small y, we are replacing with y1 in equation number 3. So that is one linearly independent solution. Now let y suffix 2 be a second linearly independent solution of equation number 3. Why? Because for every homogeneous differential equation, all solutions are the linearly independent solutions only. Okay, already we have taken that second solution. Why? Because it is a second order. Two solutions untai. If you imagine it is a quadratic equation like two roots. So here also for second order differential equation, there exist two solutions. First solution in the problem only they mentioned clearly y1 is equal to x. Second solution we are assuming that y suffix 2 be a second linearly independent solution of equation number 3, as well as that second solution is the particular integral of equation number 1. Okay, just remember carefully, y suffix 2 we are taking is a one of the solution, so that we have to be determined. So that second solution whatever we are assuming, that solution is also called particular integral. Particular integral means y suffix p. Okay, y suffix p for equation number 1. Okay, equation number 1. How you will get that value y suffix 2? This is the formula. You have to remember this formula in the order of the reduction method. So therefore y suffix 2 of x is equal to y suffix 1 into integration u of x dx. Okay, y suffix 2 of x is equal to y suffix 1 into x integration u of x dx, where it is taken as equation number 4, where u of x is a function of small x. So now our aim is we have to determine that u of x value. If you determine that u of x value, then already you know y suffix 1 of x value. If you substitute y1 of x value, u of x value in equation number 4, then automatically y suffix 2 will come, second solution. That second solution is the particular integral. So then we can write the general solution anamata. So therefore, so where u suffix of x is a function of small x to be determined. Here y suffix 2 of x, second solution to be determined, and u of x, that u of x is also to be determined. Two conditions unnai manaki. Now this method of finding yp, now whatever the procedure we are following to find that y suffix p, that is particular integral, that method is called the reduction of order method. Okay, the reduction of order method. Okay, now you are getting into the concept. Okay, so the way of finding the solution of that particular integral is called the reduction of order method. Now from equation number 4, that is from the second solution, equation number 4, we can write y suffix 2 of x is equal to, you have y suffix 1 value. What is that y suffix 1 value? Small x. Substitute that value, small x into u of x into dx. So that is taking as equation number 5. Now to find that u of x, first we are going to finding that u of x value amma. Okay, so to find that u of x value, so now you have to apply the successive derivative for equation number 5. Then you can obtain the values, then substitute them in equation number 1, then you will get that u of x value. So therefore differentiating equation number 5 twice. Okay, so why? Because in problem we have second order differential equation, that's why we are differentiating equation number 5 twice. So if you differentiate first time, first differentiation, so for equation number 5, x into u into dash. Okay, so you can take this equation number 5, you can take equation number 5, this is the u and this is the v. Okay, consider v as a integration u of x, the total term is there na, integration u of x as v, and only small x is there na, that is u. So you know very well dy dx of u into v formula. Okay, so u into v dash plus v into u dash, according to that formula, u into v dash means already integration is there, integration u of x, if you apply the differentiation, differentiation will get cancelled, you will get only u of x only. You know very well that integration differentiation is the quite opposite. Okay, so therefore plus and u dash into v, u dash means x differentiation with respect to x only, so that value 1, and v as it is integration u of x dx. Okay, so that is taking as equation number 6, first differentiation. Next, for again differentiate equation number 6 with respect to x, y2 double dash of x is equal to, now for these first two values, okay, first two values whatever you have, just these first two values, take them u into v method. Here u is small x, v is u of x. So therefore u into v dash, u is small x into v dash means u dash of x, plus u dash into v, u dash value 1, no need to write down 1, and v is nothing but u of x. So for the first term, when you apply that u into method, you will get the two terms. Next, for the second term, integration u of x dx. For this term, if you apply the differentiation, differentiation will get cancelled, then you will get the direct u of x term. Okay, so now in RHS, if you simplify x into u dash of x plus u of x plus u of x, same terms unnai here. So u of x plus u of x, you will get 2 into u of x, 2 into u of x. So that is taking as equation number 7. Now equation number 7 and equation number 8, equation number 7, equation number 6 and equation number 5. So okay, so that means y2 double dash value, y2 dash value and y2 value substitute in equation number 1. Okay, so therefore, okay, so after getting that equation number 7, continuation, substitute equation number 5, substitute equation number 5, equation number 6, equation number 7 in equation number 1, you know very well equation 5 is y suffix 2 value, equation number 6 is y suffix 2 is the first derivative, equation number 7 is y suffix 2 double derivative. So substitute is all values in equation number 1. So in equation number 1, what is that value? X square y double dash plus x into y dash minus y. So therefore in that equation number 1, this is that minus y is equal to small x. In this equation, if you substitute all those values, then it will become x square y2 double dash plus x into y2 dash minus y2 is equal to small x. Why? Because in place of small y, y2 we are replacing y2. Why? Because y2 is a solution of equation number 1. Okay, that solution we are considering as a particular integral. So then definitely that y2 also should satisfy that equation number 1. So now wherever you have y2 double dash, we are writing this value from equation number 7. So x square into y2 double dash value, x into u dash of x plus 2 into u of x, and x into y2 dash, x into y2 dash means from equation number 6, x into u of x plus integration u of x dx minus y2 of x, that is equation number 5. So y2 of x means x into integration u of x dx is equal to small x. Just we are substituting in equation number 1. So now simplify or multiply with small x each and every term, multiply with coefficient summa x cube into here u dash of x, multiply with second term 2x square into u of x plus here x into x square u of x, and multiply x into integration u of x dx. Write down this term minus x into integration u of x dx is equal to small x. Now if you observe carefully, amma, here this plus term, negative term, x into u of x dx minus x into u of x dx will get cancelled. Okay, then remaining terms, x cube into u dash of x we are writing as it is. Here 2x square and plus 1x square u of x, those two terms are similar terms, so you can add them. If you add them, you will get the 3x square u of x equal to RHS value small x. So now from the LHS, amma, you can take small x common. Okay, so therefore small x is equal, if you take common, remaining terms x square u dash of x plus 3 into x u of x is equal to RHS is small x. On both sides x cancel, amma, in LHS and RHS. Write down the remaining values. X square u dash of x plus 3x into u of x is equal to 1. Now now take x square value in LHS common. X square value in LHS common. Why? Because if you take x square common, amma, then that value will convert into, that equation convert into linear differential equation we discussed in unit 1. Okay, so therefore if you take x square common, so therefore x square into, from the first term you will get u dash of x plus in second term you have only x na. If you take x square common, amma, you will get 3 by x. 3 by x into u of x is equal to 1. Again if you multiply with x square second term, you will get the same above term only, 3 into x. Okay, so 3 by x we have. If you multiply x square, amma, x square 1x will get cancelled, then 3x only will come. Okay, so equal to 1. Now send this total x square term to RHS. So therefore u dash of x plus 3 by x into u of x is equal to 1 by x square. After sending x square value to RHS, take it as equation number 8. Now observe that u dash of x means nothing but du by dx plus 3 by x into u of x means u equal to x 1 by x square. Equation number 8. Equation number 8 we can write in this format. U dash of x means du by dx plus 3 by u of x means u equal to 1 by x square. It is purely in the format of, in this format only, which is in the form of linear differential equation in terms of u of x. Linear differential equation in u of x, that is we can write du by dx plus p into u equal to q. If you compare equation number 8 and this equation, amma, in place of p you have 3 by x value. In place of p you have 3 by x value, and in place of q, RHS, amma, you have q is equal to 1 by x square. Equation 8 and the below linear differential equation both are similar. If you compare them, you will get p is equal to 3 by x and q is equal to 1 by x square. Now the total equation 5 and its successive derivative converted into equation number 8, that is linear differential equation. Now to solve that linear differential equation, you know very well the procedure, amma, from the first unit you are studying very well. Okay, so what is the next step, amma? You have to calculate the integration factor. Why? Because equation number 8 is our last equation. So to solve that equation you have to find that integrating factor. What is that integrating factor? exponential power integration p dx. So therefore integration factor is equal to e power integration, substitute p value. What is the p value? 3 by x into dx. So therefore I into f, that is integration factor is equal to, so 3 constant take outside. Okay, so e power 3 into 1 by x dx amma. So what is the value? E power 3 into 1 by x dx, integration value log x, integration 1 by x dx log x. In the next step, if you send this 3 value to power, so therefore integration factor is equal to e power log x power 3. Okay, you know very well the formula. So integration factor is equal to, simply we can write x power 3. From this previous slide we can write here you have e power log x cube. It is in the format of e power log f of x formula. You know very well e power log f of x is equal to f of x only. In place of f of x, what is the value you have? So that is a value only in that formula. E power log f of x is equal to f of x only. In place of f of x, here you have x cube. So therefore integrating factor is equal to x cube. So after getting integration factor, what is the next step? General solution of equation number 8 is given by, so this is the formula, u into integration factor is equal to integration of q into integration factor dx plus c1. So now substitute the corresponding values in the general solution u as it is u only. Why? Because here variable is in terms of u, so we are writing u. And integration factor x cube is equal to integration q value 1 by x square and integration factor value x cube dx plus c1. Here x square will get cancelled, 1x will remain in RHS. So therefore LHS ux cube is equal to integration x dx plus c1. Okay, plus c1. So therefore ux cube is equal to integration x value, integration x dx. You know very well integration x power n dx is equal to x power n plus 1 by n plus 1 plus c. This is the formula. Here x power 1, so therefore n is equal to 1. If you substitute n is equal to 1 in the above equation, then x square by 2 is the value, x square by 2 plus c1. So now send this x cube value to RHS, or otherwise on both side divide with the x cube, on both side divide with the x cube, then you will get u equal to, small u is equal to, if you divide with the x cube on both side, if you divide with the x cube on both side, so x cube will get cancel, u is equal to, okay, so 1 by 2x plus c1 by x cube. That is taken as equation number 9. What is that? That is the value of u of x term. U of x is equal to function of in terms of x ani manam chusam kada after writing equation number 4, that is y2 of x value, where u of x is the, I will show to you. Okay, so u of x is a function of x ani cheppam kada, so that u of x value we determine now. After determining so now you can see, so equation number 9, substitute equation number 9 in equation number 5. So therefore y suffix 2 of x is equal to x into, in place of u of x, so we are substituting that RHS of equation number 9 into dx plus c1. Okay, there is no c1 term, just ignore that value. So therefore y suffix 2 into x is equal to x into, separate that integration value 1 by 2 into integration 1 by x dx plus c1 into integration x power minus 3 dx. Okay, so just ignore this value, not, there is no plus c1. Okay, so therefore y suffix 2 is equal to x by 2. X by 2 integration 1 by x dx value log x plus c1 into, okay, so here you can write we are multiplying directly with, if you multiply with x c1 into x and integration of x power minus 3 value x power minus 2 by minus 2. Why? Because you know very well formula, x power minus 3 plus 1 by minus 3 plus 1. When you have that formula, integration x power minus 3 dx. So by using that formula, x power minus 2 by minus 2 plus c1. Okay, there is no c1. So therefore y suffix 2 is equal to x by 2 log x. So here you have x power 1 and x power minus 2. That means x power minus 1 will come. If you send that value, x power minus 1 value, if you send that value it will become 1 by x. That means minus 1 by 2x into c1. This is the y suffix 2 value. What is that y suffix 2, amma? That is a particular integral. Okay, we are taking it as equation number 10. So therefore, we got that first solution y1 of x is equal to small x. Okay, it is one independent solution. Recently we got that equation number 10 y suffix 2. Okay, so that is another solution. Now general solution of equation is given by small y is equal to c1 y1 into x plus c2 into y2 of x. For every problem based on this method, this is the equation for the general solution, c1 y1 of x plus c2 into y2 of x. So therefore y is equal to c1 y1 of x value small x plus c2 into y2 of x value x by 2 log x minus c1 by 2x is the required general solution of the given second order linear differential equation of non-constant coefficient. So in this format you have to determine. The process is very easy, amma. First of all, in the problem only they will mention the solution y1. So that solution trivially you have to take as y1. So our aim is you have to calculate the second solution y2. This y2 you have to consider as a particular integral y suffix p. So therefore y suffix p is equal to, what is the formula, amma? y1 into integration u of x dx. Already you have y1 value. Now our aim is we have to determine u of x value. To determine that u of x value, apply that the first derivative for the y2, apply the second derivative for the y2 and substitute them in equation number 1. Then you will get u of x value. Okay. After converting into linear differential equation, you will get integration factor. After that general solution. Then you will get u of x value. Substitute this u of x value in y suffix 2, in y suffix 2. So then you will get a particular integral value. So that particular integral is the second solution. Now substitute first solution y1, second solution y2 in the given equation y is equal to c1 y1 x plus c2 y2 x. So then that is the required solution of the problem. Okay. So this is the total explanation of this problem, amma. Very important problem. Repeated so many times in the examination. Make a perfect practice. Prepare well. Until bye. Thank you.